What is going on, everybody, and welcome to a much needed update to the deep learning in Python with TensorFlow as well as now Keras tutorial. It's been a bit over 2 years since I did just a basic deep learning video in Python, and since then a lot has changed. It's now much simpler to both get into it, but then also just to work with deep learning models. So if you want to get into the more nitty-gritty details and the lower level TensorFlow code, you can still check out the older video, but if you're just trying to get started with deep learning, that's not necessary anymore because we have these nice high-level APIs like Keras that sit on top of TensorFlow and make it super simple. So anybody can follow along. If you don't know anything about deep learning, that's totally fine. We're going to do a quick run through of neural networks. Also, you're going to want Python 3.6, at least as of the release of this video. Hopefully very soon. TensorFlow will be supported on 3.7 and in later versions of Python. It just happens to be the case right now. It isn't. I think it's something to do with the async changes. I'm not really sure. Anyways, let's get into it, starting with an overview of how neural networks just work. All right, to begin, we need to have some sort of balance between treating neural networks like a total black box that we just don't understand at all and understanding every single detail to them. So I'm going to show you guys what I think is just the kind of bare essential to understanding what's going on. So a neural network is going to consist of the following things. Like what's the goal of any machine learning model? Well, you've got some inputs, so let's say x1, x2, x3, and you're just trying to map those inputs to some sort of output. Let's say that output is determining whether something is a dog or that something is a cat. So the output is going to be 2 neurons in this case, so it's just boom, 2 neurons. Now what we want to do is figure out how are we going to map to those things. We could use a single hidden layer. Let's say we're going to do some neurons here. And that's our first hidden layer. Now, what's going to happen is each of these x1, x2, and x3, these are going to map to that hidden layer. Each of the input datas gets connected to each of the neurons in that first hidden layer. And each of those connections has its own unique weight. Now from here, that first hidden layer could then map and connect to that output layer. The problem is if you did this, the relationship between x1 and dog or cat and all the other ones, those relationships would only be linear relationships. So if we're looking to map nonlinear relationships, which is probably going to be the case in a complex question, you need to have 2 or more. One hidden layer means you just have a neural network. 2 or more hidden layers means you have a quote-unquote deep neural network. So we'll add 1 more layer, and then we're going to fully connect that one too. And then once that's fully connected, again, all unique weights, each of those blue lines has a unique weight associated with it, and then that gets mapped to the output. And again, each blue line has a unique weight associated with it. So now what we're going to do is talk about what's happening on an individual neuron level. So again, that neuron has certain inputs coming to it. It might be the input layer X values, or it could be inputs coming from the other neurons. So we're again going to call the inputs X1, X2, and X3, but just keep in mind, this could actually not be, it might not be your input data, it might be data coming from another neuron. But regardless, that data is going to come in, and we're just going to get the sum of that data. So it's going to come in and be summed all together. But remember, we also have those weights. Each of the inputs has a unique weight that gets put, multiplied against the input data, and then we sum it together. Finally, and this is kind of where the artificial neural network comes into play, we have an activation function, and this activation function is kind of meant to simulate a neuron actually firing or not. So you can think of the activation function like on a graph. You got your X and your Y. And then a really basic activation function would be like a stepper function. So if X is greater than a certain value, boom, we step up and we have a value. So let's say here this is 0, here the value is 1. So let's say this is our X-axis, 1, 2, 3. So if X, after being all the inputs are multiplied by their weights, summed together, if that value is, let's say, greater than 3, well, then this activation function returns a 1. But today we tend to use more of a sigmoid activation function. So it's not going to be a 0 or 1. It's going to be some sort of value between 0 and 1. So instead, we might actually return like a 0.79 or something like that. So coming back to this neural network here that we've been drawing, let's say here on this final output layer, you've got dog and cat. Well, this output layer is almost certain to have just a sigmoid activation function. And what it's going to say is maybe dog is a 0.79 and cat is a 0.21. These two values are going to add up to a perfect 1.0, but we're going to go with whatever the largest value is. So in this case, the neural network is, you could say, 79% confident that it's a dog, 21% confident it's a cat. We're going to take the argmax basically, and we're going to say, we think it's a dog. All right, now that we're all experts on the concepts of neural networks, let's go ahead and build one. You're going to need TensorFlow, so do a pip install -- upgrade TensorFlow. You should be on TensorFlow version 1.1 or greater. So one thing you can do is import TensorFlow, and then actually TensorFlow as TF, and then tf.version will give you your current version. So mine is 1.10. Now, let's go ahead and get started. So the first thing we're going to do is import a data set. We're going to use MNIST, kind of the hello world example of data sets with machine learning. It is a data set that consists of 28 by 28 sized images, so that's like the resolution. Images of handwritten digits 0 through 9. So it'll be like a 0, 1, 2, 3, and so on. And it's a handwritten kind of unique image. So it's actually a picture, and we can graph it soon enough so you can see it's actually an image. And the idea is to feed through the pixel values to the neural network and then have the neural network output which number it actually thinks that image is. So that's our data set. And now what we want to do is unpack that data set to training and testing variables. So this is a far more complex operation when it's actually a data set that you're kind of bringing in or that you built or whatever. For the sake of this tutorial, we want to use something real basic like MNIST. So we're going to unpack it to xtrain, ytrain, and then we're going to do xtest, ytest. And that's going to equal mnist.load_data. So that's going to unpack it into there. Now, just to show you guys what this is, we're going to use matplotlib. You can pip install or just look at it with me. But we're going to import matplotlib.pyplot as a PLT. And what we're going to do is plt.imshow, and we're going to do xtrain, and we'll do the 0th. So one thing we could do, just for the record, let me just print. So you can see what we're talking about here. So this is just going to be an array. It'll be a multi-dimensional array, which is all a tensor is, by the way. So here's your tensor, right? Okay, so that's the actual data that we're going to attempt to pass through our neural network. And just to show you, if we were to actually graph it and then do a plt.show, it's going to be the number, and you can just excuse the color. It's definitely black and white. It's a single color. It's a binary. So one thing we could say is the color map is equal to plt.cm for color map, binary, replot it, and there you go. It's not a color image. So anyways, back to our actual code up here. Once we have the data, one thing we want to do is normalize that data. So again, if I print it out, you can see it's data that seems to vary from 0 to, looks like we have as high as 253. It's 0 to 255 for pixel data. So what we want to do is scale this data or normalize it. But really what we're doing in this normalization is scaling it. So we're going to just redefine xtrain and xtest, but it's going to be tf.keras.utils.normalize. And we're going to pass xtrain, and it'll be on axis 1. And then we're going to copy, paste, and we're going to do the exact same thing for xtest. And all this does, let's just run that, and then we'll run this again. And you can see how the 5 has changed a little bit. It looks like it got a little lighter. And then we come down here and we can see the values here are now scaled between 0 and 1. And that just makes it easier for a network to learn. We don't have to do this, but at the end of this, we probably won't have time, but if you want, comment those lines out and see how it affects the network. It's pretty significant. Okay, so the next thing we're going to do now is actually build the model. So the model itself is going to start as tf.keras.models. And then it's going to be the sequential type of model. There's two types of models. The sequential is your most common one. It's a feed forward like the image we drew. So we're going to use this sequential model, and then from here we can use this like model.add syntax. So the first layer is going to be the input layer, and now right now our images are 28 by 28 in this like multi-dimensional array. We don't want that. We want them to be just like flat. If we were doing like a ConvNet or something like that, we might not want it to be flat. But in this case, we definitely want to flatten it. So we could use that. We could use like NumPy and reshape, or we can actually use one of the layers that's built into Keras, which is flatten. So we're going to do add, and what we're going to add is tf.keras.layers.flatten. So one of the reasons why you want this to actually be a layer type is like when you have a convolutional neural network, a lot of times at the end of the convolutional neural network, there'll be just like a densely connected layer, and so you need to flatten it before that layer. So it's used for more than the input layer. We're just going to use it for the input layer, just to make our lives easier. So once we've got that, that's our input layer. Now we want to do our hidden layers. Again, we're going to go with, I think, just 2 hidden layers. This isn't a complex problem to solve. So again, we're going to use the model.add syntax, and we're going to add. And in fact, I think what I'm going to do is just copy, paste, and then rather than a flattened layer, it's a dense layer. In the dense layer, we're going to pass a couple parameters here. So the first one's going to be how many units in the layer. So we're going to use 128 units, or 128 neurons in the layer. Then we're going to pass the activation function. This is like the function, like I said, like a stepper function or a sigmoid function. What is going to make that neuron fire or sort of fire or whatever. So we're going to use tf.nn.relu for rectified linear. This is kind of the default go-to activation function. Just use it as your default, and then later you can tweak it to see if you can get better results, but it's a pretty good one to always fall back on. So we're going to add the second one just by copying and pasting. Again, I'm going to add a final one, and this is our output layer, which is still going to be a dense layer. It's not 128. Your output layer will always, if it's in the case of classification anyways, it'll have your number of classifications. In our case, that's 10. And the activation function, we don't want it to be ReLU because this is like a probability distribution. So we want to use softmax for a probability distribution. So that is our entire model. We're done with defining, the architecture, I guess, of our model. Now what we need to define is some parameters for the training of the model. So here we're going to say model.compile, and in here we're going to pass the optimizer that we want to use. We're going to pass the loss metric, which loss, we haven't really talked about it. Loss is the degree of error, basically. It's what you got wrong. So a neural network doesn't actually attempt to optimize for accuracy. It doesn't try to maximize accuracy. It's always trying to minimize loss. So the way that you calculate loss can make a huge impact because it's what's loss's relationship to your accuracy. Optimizer. Okay, so the optimizer that we're going to use is going to be the atom optimizer. You could use something. This is basically this is like the most complex part of the entire neural network. So if you're familiar with gradient descent, you could pass something like stochastic gradient descent, but the atom optimizer, kind of like the rectified linear, is just kind of the default go-to optimizer. You can use others. There's lots of them. Not lots, but I don't know, 10 or so in Keras anyways. So anyways, there's other ones to go with. Atom seems to be the one that you should start with. For loss, again, there's many ways to calculate loss. Probably the most popular one is categorical cross entropy, or some version of that. In this case, we're going to use sparse. You could also use binary, like in the case of cats versus dogs. You would probably use binary in that case. But you could just kind of blanket categorical cross entropy everything. Anyways, then finally, what are the metrics we want to track like as we go? And we're going to just do accuracy. Okay. So once we have all this, we're actually ready to train the model. So to train, it's just model.fit, and then you're going to pass what do you want to fit? So xtrain, X test. I'm sorry, Y. Okay, X train, Y train, and then epochs 3. Total brain fart. Okay, let's go ahead and run that. And we should start to get some training. Hopefully it doesn't crash me as I'm recording, but okay, looks good. Let's zoom out just slightly so it looks a little better. And we can see actually our accuracy is already quite well. Our loss is also still dropping, so our accuracy should still be improving, and sure enough it is. Awesome. Okay, so we did pretty good. We got a 97% accuracy after only 3 epochs, which is pretty darn good. So once we have this, we can, this was in sample, so this is always going to really excite you. But what's really important to remember is neural networks are great at fitting. The question is, did they overfit? So the idea or the hope is that your model actually generalized, right? It learned patterns and actual attributes to what makes an 8 and what makes a 4, rather than memorizing every single sample you passed. And you'd be surprised how easily a model can just memorize all the samples that you passed to do very well. So the next thing we want to always do is calculate the validation loss and the validation accuracy. And that is just model.evaluate, evaluate, X test, Y test. And then we'll go ahead and just print val loss and val accuracy. And we can see here the loss is almost 0.11 and the accuracy is at 96.5. So a little less than the one that we ended on, and the loss is quite a bit higher relatively, but you should expect that. You should expect your out of sample accuracy to be slightly lower and your loss to be slightly higher. What you definitely don't want to see is either too close or too much of a delta. If there's a huge delta, chances are you probably already have overfit and you'd want to kind of dial it back a little bit. So that's basically everything as far as the basics of Keras and all that. The only other things that I wouldn't mind covering here is, like, if you want to save a model and load a model, it's just model.save, and we can save this as epic num reader.model. And then if you want to reload that model, we'll save it as we'll call it a new underscore model. That's going to be equal to tf.keras.models.load model, and it's this exact model name. Whoops, there we go. So that's our new model. And then finally, if we wanted to make a prediction, we could say predictions equals new model.predict. And keep in mind, predict always takes a list. This will get you a few times for sure. But anyways, that'll take a list, and we'll do x underscore test. And then if we just print predictions, it's probably not going to look too friendly. It's a little messy. So what's going on here? These are all one-hot arrays, and these are our probability distributions. So what do we do with these? So I'm going to use NumPy. You can also use tf.argmax, but it's an abstract, it's a tensor, and we have to pull it down. We need a session and all that. It's just easier to import NumPy, at least for this tutorial here. Import NumPy as np, and then print, for example, np.argmax. Let's do predictions, and let's just do the 0th prediction. Okay, it says it's a 7. So the prediction for x test 0, like the 0th index, it's a 7. So, gee, if only we had a way to draw it. Okay, we can definitely do this. So we can do plt.mshow, and we're going to do x test 0th, and then plt.show. Oh, look at that. It's a 7. Okay, so I think that's basically all the things I would want to show you guys as far as like just a quick and quick start with deep learning and Python and Keras and TensorFlow. This just barely scratches the surface. There's so many things for us to do. I definitely plan to have at least one more follow-up video covering things like loading in outside data sets, definitely some TensorBoard, reading the model, understanding what's going on and also what's going wrong, because that's eventually, it's really fun when we're doing tutorials and problems are like already solved and we know the answer. It's very exciting, but in reality, a lot of times you have to dig to find the model that works with your data. So anyways, that's definitely something we have to cover, or at least that you're going to have to learn somehow or other. Anyway, that is all for now. If you got questions, comments, concerns, whatever, feel free to leave them below. Definitely check out reddit.com/r/machine learning, the Learn Machine Learning subreddit. You can come join our Discord if you got questions. That's just discord.gg/Centex. We'll get you there. Also, special thanks to my most recent channel members, Daniel, Jeffrey, KB, Abhijit, Hner, Newcastle Geek, Fuba44, Jason, and 8 Counts. Thank you guys so much for your support. Without you guys, I couldn't do stuff like this, so really thank you. Anyways, that's it for now. More to come at some point. Till next time.